All right, guys. In this video, I want to do an example. And what I'm going to imagine is the following situation. We have a slide, something with no friction. I don't want to worry about friction. And I just want to point out something that's kind of interesting. So let's imagine we have a slide, which is like this. Oh, you get to the bottom. So we can have a little kid there going down the slide. And let's say that the height here is 3 meters. And let's say, well, it really doesn't matter. 3 meters, and let's say that the mass of the child is, I don't know, 20 kilograms. Okay? And you could also imagine a situation where you had a slide which was the same height, shallower, same height, but shallower. So you would have you'd have smaller forces. On the other hand, the forces act over a much greater distance. And what I would like to do is have you use work energy theorem in both cases, assuming everything else is the same. And let's just go through the analysis to find the velocity starting from rest at the bottom of the hill. So let's remind ourselves, the formula for kinetic energy is 1/2 the mass times velocity squared. And the formula for potential energy due to gravity is mg times y minus y reference. Okay, so we're going to start at 3 meters. We're going to finish at a height of 0. Now you can choose the reference height however you want. So what we're going to do is choose the reference height. Let's choose the reference height. So, well, let's just do it the easy way. Choose the reference height so that the potential energy is 0 at the bottom. That's the smart way to do it. So that's easy. When the height is 0, then we'll say that the energy is 0, so therefore the reference height is 0. Excuse me. I emphasize, though, you get the same answer if you choose any other point. And there's a sapling question where you've got blocks of weird shapes on different stair steps. And they'll say, blah, 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 blah. This configuration has energy, potential energy 5. Well, what they're really telling you to do is to use that fact to solve for the reference height. And then once you solve for the reference height, you can get everything else that they ask. Okay, so let's do that. So in both cases, we can handle them the same way. So I'm going to make my system be the child and the earth. So gravity is going to be part of the system. Okay, so if the system is the child and earth, I have to write down all the forms of energy that are relevant for the child and earth. So we have kinetic energy of the child, and we have potential energy due to the gravitational interactions. And I will say then, I would have, after I write down my system, I write down the work energy theorem. So it's going to say the change in kinetic energy plus the change in potential energy. That equals the work being done on the system from the outside. Now, if there's no friction, then there's really no outside forces acting on the system. It's just the child and the earth. There is no work being done. So the work is going to be 0. We would say that the mechanical energy is conserved. It's not changing. Okay, that's fine. And let's go ahead and work this out. We'd say this is 1/2 mv final squared. The initial velocity is 0, so I get minus 0 plus mg times y final minus y ref minus mg y initial minus y reference. Now I'm choosing the reference height so that the potential energy is 0 at the bottom. That means I set the reference height to be 0. And the final height is 0 because they land on the ground. Notice how I start with a very abstract formula. I plug in using my formulas, my expressions, and I just start setting things to 0. That's usually what happens. You start with a big, ugly equation, but then you end up putting a lot of things to 0. So it ends up not being as bad as you think it might have been. Okay. Oh, look, and it's a simplification because everything comes with a mass. So I can divide that through. So I didn't need to know the child's mass in the end. And I finally can determine the velocity because I get v final squared equals 2g y initial. Oh. Sorry, jumped the gun. Minus y initial equals 0. And then I turn that around and get v initial, or v final equals the square root of 2g y initial. There you go. So what's happened is in this story, the child starts out with a lot of potential energy. There's a lot of stored energy in being up high. There's a lot of potential for motion. And as the child goes down the slide, the child loses potential energy, but gains kinetic energy. Same thing happens here. Notice, when we write the formulas using potential energy, it's immediately obvious that the angle doesn't matter. The only thing that matters is the initial height and the final height. If you evaluate work, it's not as clear. You end up with some trigonometry and an intermediate step that cancels out in the end. So if you can, use potential energy concepts and it makes things simpler. Let's finish this off and get some numbers. I said that y initial is 3. So that makes this pretty much the square root of 60 meters per second. And now if I think about that, 8 times 8 is 64, 7 times 7 is 49. So it's a little closer to 8 times 8 than it is 7 times 7. So I'm going to guess something like 7.75 or something like that, 7.7. Let's check. I've got a calculator here. See how that goes. Oh, dear. 60 square root 7.74. 7.75, not too bad. Okay, close enough. All right, so that's kind of an archetypical sort of problem you would solve with potential energy ideas. And you in each problem, you get to choose the reference height one time. It's not a physical quantity, only differences in energy matter. After you fix that reference height, you have to live with that choice. You can't keep changing it and keep setting potential energy equal to 0 at all points in the problem. Well, then you're basically saying that there's no such thing as potential energy, and that's not right either. Okay, so potential energy, you can set it to 0 at one point in space. And then after you choose that reference height, the reference position, it needs to be 0 forever. Very good.